straight out, but people in the business tell me that a lot of students think it's going to go straight out, radially outward. Get the picture? Of course not. It's going to keep going with whatever velocity it had just a moment before the string broke. That is to say, it will go along tangentially. So that's and how it's supposed to be an application of Newton's first law of motion, I guess. That something keeps going with the same original velocity if there's no force acting on it. But our business for today, and pretty much for Monday also, is Newton's second law of motion. The fundamental law governing classical mechanics says F is equal to ma, although typically it's the a that you're trying to calculate, not the F. You know the force that's applied to some object and you know what its mass is, and you're trying to figure out what the acceleration is. That would be the more typical situation. Notice that this is a vector law. Which is to say that it really is shorthand for three separate equations, one in the x direction, one in the y direction, and one in the z direction. Three separate equations. And sometimes it's handy in working out a problem to realize that you can work in the vertical dimension and also in the horizontal dimension, that is giving you two different equations, or in three dimensions, three. Another point to be made about this, obviously, the force here that's acting on the object, if there's several forces acting, I mean the vector sum. So your first order of business is to add those forces up as vectors, add those forces up, and the total force acting on the object is going to determine its acceleration. Last time I was in the process of making a list of kinds of forces. One, the force of gravity in this room, or what we call weight. And g, the mass of the object times the acceleration of gravity, 9.8 meters per second squared. That's the weight of an object, and of course it points down. A second type of force, tension. That's the kind of force exerted by a string or rope. Usually use the letter T for it. And the only important thing to remember about tension is that ordinarily tension is the same all the way down the line. It's not, 5 newtons at this end and 7 newtons at the other end or something. The only exception to that is if the rope itself has substantial mass. Ordinarily, we pretend that ropes and strings are massless. And if it doesn't say in the problem that the rope is massless, then probably you're supposed to assume that the rope is massless. If the rope has mass, then the tension varies as you go along the line because the changing tension is responsible for accelerating the rope itself. So if you put a little spring gauge into the rope, bust it open and tie a little spring gauge in there, you would measure the same tension T anywhere down the line. And for that matter, if the rope passes over a massless, frictionless pulley, then the tension is still the same. It's pointing in a different direction to be sure, but it's still the same. Third type of force we encountered, normal force. Silly word, but no, maybe not so bad. Perpendicular force would be a little bit better. We use the letter N for that. That's a force that acts between two surfaces that are in contact, like between this block of wood and the table. They're in contact, and the normal force acts perpendicular to the surface. Normal is a code word meaning perpendicular. So, those are the three types of forces we have encountered so far. Later on, we'll get some other ones, the force of friction, and the force exerted by a spring, for example. But this will do it for now. What I'm going to do for the rest of the class today is run for you a string of, I've got an arsenal of 7 different examples here. I'm not sure whether I'll hit all of them. But my point is not so much the details of each particular example as to use them as vehicles to explain general strategies. So from time to time I'm going to pause and give you advice about setting up problems that may or may not help. Use it if it does, and ignore it if it doesn't. So, example 1, the one that we were talking about at the end last time. Block of wood sitting on a table. What forces act on that? For today, forces are written. Here's the block of wood. It has a mass m, let's say. What forces act on it? Answer, weight, of course. It's weight acting down, mg, and normal force acting up. That force was exerted by the table, pushing up on the book. I once had a little idea about this. Let me tell this story and then we'll come back to your question. I don't know whether this will convince you that there's such a thing as a normal force pushing up on that brick or not, but at least sometimes it seemed to me that it proves something. Suppose that I stuck a soft P between the brick and the book. So imagine a half-cooked pea, and I stick it under there. What would that look like? I reckon it would flatten out like that. Flattens out on the top and flattens out on the bottom. Who flattened it on the top? The brick pushing down. Who flattened it on the bottom? The table pushing up. That's the normal force. You wouldn't expect to see that P in this shape here, would you? Flattened on the top only because only the top is pushing down. No, flattened on both sides. Book pushes down from the top, table pushes up from the bottom. Squishes the P on both sides, flattens it on both sides. Does that prove anything to you? Anyhow, there is a normal force, and in fact, that normal force is equal to mg. How do I know? Because the brick isn't moving anywhere. No acceleration means net force has got to be equal to 0, so the normal force is equal to mg. Now you got it.
That was my question.
Okay. By the way, be a little bit cautious about this. Probably in 75% of all problems you encounter, the normal force is equal to mg because it's a configuration like this. But there is no law of physics that says normal forces have to be equal to mg, nor any law of physics that they have to point in the vertical direction. They point perpendicular to the surface of contact. If you're on a sloping surface, then they're going to point perpendicular to that surface, not straight up. And they're not, in general, equal to mg. In fact, you saw an example of this, although I'm not sure you thought it through because it wasn't relevant to the problem, but on the third owl for today was a situation in which some person is pulling a crate or something or other across the floor here. So here's the crate, and it has a mass m, and the person is pulling on it with a rope that makes an angle of theta here, and they're pulling with a tension T in the rope. Whoops, I said forces were red. So, okay, let's put the forces into this diagram as they were on that owl. Do you remember? There's a tension T, of course, exerted by the rope, for sure, pulling up like that. What other forces act on that crate?
Friction.
Friction, they said that there was a backward force of friction here. I'll just call that F. Due to the floor pulling on that thing, pulling backward on it, because the guy is driving it along to the right. What else? Gravity, always a safe one. Gravity mg acting down, normal force acting up. Now here is where, if you're careless, you immediately jump to the conclusion normal force equals mg. Not true in this problem. Are there any other forces acting on this thing now besides those?
The X1 component.
Ah, no, those are not forces, those are components of forces. So you're one step ahead of the game. You know what? I feel silly making this sermon, but this is easy stuff, ridiculously easy. The danger of it is that you start thinking too much. And if you think too much, you start doing the next step before you're done with the previous step, and that's where you're likely to get into trouble. So, suppose that somebody says, well, there's not just this tension here, that tension is pulling partly in the horizontal direction. I'll put in T times the cosine of theta, that's the horizontal component of that tension. And there's the vertical component of that tension, T times the sine of theta. Very dangerous, because now you've counted the same force twice, right? It was that tension pointing along the diagonal line, and it's two components of the tension. I don't care which way you do it. Personally, when I'm drawing the diagram, I stick in the forces and only the forces. I don't talk about components of them. I don't look left or right, just the forces. So I'm going to put these actually the components here, because what was said was right. It's just a little ahead of the game. I'm going to put those in yellow so that red is only the forces, and these happen to be two components of that same force, right? But don't count that as a separate, don't count those as separate forces. Okay, let's write down now Newton's second law in both dimensions. This is an example of a two-dimensional problem. There's the vertical dimension and the horizontal dimension. In the horizontal dimension, what do you see? What forces act?
Friction and
There's friction in the backward direction, and there's a hunk of the tension, the horizontal component of the tension, pulling in the forward direction. So let's write it like this. T cosine of theta, that's the forward component of the tension, minus the friction pulling back, and that's supposed to be equal to the mass of this object times its acceleration. So there was the equation that you needed on the owl. I think that it asked you to find the acceleration, didn't it? So just divide through by m, and that will tell you what the acceleration of this object is. How about in the vertical direction? This it did not ask about, but it probably should have, because it's an interesting question. In the vertical dimension, what do I see here? Acting up first. You tell me, what forces do you see pulling up on this thing? Forces or components? And that pulls it up. T sine theta also pulls it up. And how about in the downward direction?
mg.
mg, of course, so I put that in with a minus sign. That's the sum total of all the forces acting in the vertical direction. That is, well, very good. It's mass times acceleration. Acceleration in the vertical direction. This thing isn't moving in the vertical direction, so the acceleration there is 0, right? In general, it would be m times a, but in this instance, the a is obviously 0. Got the picture? So if somebody said to you, what is n in this problem? What is the normal force acting on this crate? The answer would be n is equal to, pulling this stuff over to the other side, mg minus t sine theta. How about that? It's not just mg, it's a little bit less than mg. Why physically did the normal force come out to be less than mg? Well, somebody's saying, because the tension, the rope here, is pulling upward somewhat, not completely, but it does have a vertical component, and that's sort of relieving part of the weight. That's canceling part of the weight, so the normal force is just taking up the pieces and doing what's left over. So there's an example of a case in which the normal force does act perpendicular, does act vertically upward, of course, because it was a horizontal surface, but it's not in the magnitude mg. No guarantee that it will be mg in general. Got the picture? So be very careful about this. When you stick in normal forces, do not leap to the conclusion that that normal force is equal to mg. Probably it is, but take a close look at the situation. The normal force is going to do whatever it has to do to keep that thing from moving in the vertical dimension. Okay, example 3. What's my example 3? Atwood's machine. Actually, I'm going to stick that up this side because it needs some more space. Always kind of wondered who Atwood was. Atwood's machine consists of 2 masses hanging from a pulley. So I got a pulley suspended from the ceiling. There's the ceiling, pulley, and now I've got 2 masses hanging from it. One on this side I'll call M1, and then it goes over this massless frictionless pulley, as you can see, clearly massless frictionless, and rope also, a nice massless rope, and down here I've got M2 dangling from that side. I let the thing go. What happens? Obviously, the heavy one goes down and the light one goes up, right? I'm sort of setting up a demonstration, but I don't think you need a demonstration for that. The heavy one goes down, the light one goes up. Question, what's the acceleration of that system? By the way, the same acceleration for both of them, isn't that right? However, this one goes down, the other one's got to go up by exactly the same amount. So the 2 accelerations will be the same, although one of them upward and one of them downward. Okay, what's the acceleration? First order of business, draw the 2 subsystems separately. I'll make a little list here of strategies or procedures. Draw the subsystems. In the previous 2 examples, there was only one subsystem, so there it is. Draw the subsystems showing forces that are acting on each one. So here's the subsystem number 1 is M1, and here's M2. That's 2 separate subsystems. You tell me, forces acting on M1 over here. The tension pulling up, that's the tension in the string, and of course, gravity, M1G, acting down. Anything else?
No.
How about the gravity acting on M2? No, that doesn't belong in this diagram. Completely different diagram, right? I'm just talking about M1. I see 2 things pulling on M1. Gravity pulling down, tension pulling up, period. That's it. Now we go to M2. What forces do I see acting on M2? Gravity acting down, that's M2 times G. Tension. That's the tension over here acting on number 2. Same as the one acting on number 1? Yep, same rope, massless rope, went over frictionless, massless pulleys. I didn't write that down, but it's the case. So that's the same tension T because it's the same piece of rope. Okay? Any other forces acting on those 2? Nope. I don't think so. Good. Now I'm ready to write down Newton's second law of motion. I have to decide which is the positive direction for each one, because I could say the net force on this is T minus M1G. Would that be correct? Absolutely. Or I could say it's M1G minus T. Would that be correct? Absolutely. Just depends on which way you call positive. How should we decide which way to call positive? Personally, what I do at this point is I make a guess. What direction do I suspect that the acceleration actually is in? Let's say, for the sake of argument, that M2 is the heavier one. Then this one is going to accelerate downward. I'm putting this in green because it is not a force. This is an acceleration. The acceleration looks like it's going to be downward for this one and same acceleration upward for this one here. So I indicate the accelerations in there, not on my original diagram, not certainly with the red ink, because that tells me about forces. An acceleration is not a force. But just to tell me, just to inform me what direction I think the acceleration is going to be, or rather, to establish by convention, what's the positive direction for each of those masses. Having established that convention, suppose that I guessed wrong. Suppose that the acceleration turned out to be the other way around. Big deal. It's going to come out, when I do all the calculations, it's going to come out a negative number. When I see that minus sign, I say, oh, well, I guessed wrong, and it was the other way. So it doesn't matter how you establish the convention at the beginning. I would always go for the convention that seems most likely to be the positive one. But as long as you're consistent, it's not going to matter if you actually guessed wrong.
I just the tension thing. I thought the tension of M1 was going to be greater than the tension of M2.
No. You say the tension of M1 and M2. I'd say the tension of the string. It's the string that the tension pertains to. And remember the rule about tension. If it's a massless string and massless frictionless pulleys, then the tension is the same all the way along the line.
If it had mass, would M1 have more tension than M2?
That's right. Yeah. Yeah. Or if the pulley, if the pulley had mass. We'll come back actually later on when we've talked about rotation. The reason we can't give the pulley mass right at the moment is that that's a rotational system, and we haven't done rotational dynamics yet. When we come to rotational dynamics, we can stick that in, and you'll see exactly. Then when we do this same problem, but with a massive pulley, we will call this T1, and we'll call this T2, and one of the things of interest will be to find out how T1 and T2 differ. So, where are we? Having established the conventions like this, now watch how I write down Newton's second law. Write Newton's second law for each object. What's Newton's second law say for this one? The positive direction is upward. Pulling upward is T. Pulling downward, therefore with a minus sign, is M1G. That's equal to, this is the net force in the conventional positive direction. The net force, T minus M1G, is equal to, you tell me. MA, I agree. Which M? M1A. Now, a lot of people say at that point, no, wait a minute, this is attached also to M2. I've got to accelerate the M2 too. So shouldn't I maybe sneak in a little bit of M2 in there, like write M1 plus M2A or something? No, I'm just talking about the forces acting on M1. That's equal to the mass of M1 times A. I'm not even thinking about what's happening elsewhere. Of course, the message is communicated via the string and the tension. The M2 is going to come into the final answer somewhere. But when I'm talking just about the motion of M1, then it's M1 times A. Total force acting on M1 is equal to M1 times A. Don't even be thinking about M2. That's not relevant to this part of the problem. Now we come to M2. What's the positive direction for M2? Downward. Therefore, how should I write the total force acting on it? M2 times G, which pulls in the downward direction, minus T, which pulls in the upward direction. And therefore, on this side of the equation, becomes negative, is equal to, that's the net force, it's equal to the mass. Whose mass? M2. That's the only one we're talking about, times the acceleration of number 2. Fair enough? Now, when you look at these two equations, if you have not carefully indicated the positive directions that you're counting for acceleration, you might be inclined to say, hey, these are inconsistent. Here he said the net force is T minus M1G. Here he said the net force is M2G minus T. Seem to be backwards. It is backwards because the conventional direction for A was backward in the 2. There's another way that you could do business here, by the way. You could say, I always define my acceleration positive upward. Okay? Then you would call this one A1, and you would call this one A2, and then you would have a third equation which would say A2, by the way, is equal to minus A1. You could do business that way, and maybe it would be a little bit more systematic, but personally, I like to do it to incorporate the knowledge about the two accelerations being coupled right into the equation of motion this way, but that is a matter of choice. Okay, what do I want to calculate here? I never told you what the question. Oh yes, the question is what's the acceleration? How should we get the acceleration? I've got two equations, one here, two unknowns. T, the tension, and A, the acceleration. You see a quickie way to get rid of the T? That's what I'm not interested in this problem. How about if I added the left sides? What if I added these two equations together? Then on the left side I would get T minus M1G plus M2G minus T. The T's would cancel out, and I would get, well, I'll write it down. T minus M1G. T minus M1G plus M2G minus T, that's the sum of the left-hand sides, is equal to the sum of the right-hand sides, M1A plus M2A. The T's here nicely cancel out. I could rewrite this equation, I guess, factoring out the common factor of G on the left. G times M2 minus M1 is equal to, and factoring out the common factor of A on the right, M2 plus M1. And therefore A dividing through by the factor here is equal to G times M2 minus M1 over M2 plus M1. Did both masses come into the final answer? Well, of course they did. But they didn't come in at the level of writing Newton's second law for each piece separately. Seeing enough on that? What if M1 was actually bigger than M2? If M1 was bigger than M2, this is the heavier mass, then A would have come out negative, right? That would indicate that I guessed wrong over here, that A was not going up for this one, it's actually going down for this. Well, of course, yeah, if one was heavy, that's the way it would go. So the sign of the A is going to tell you which way it actually goes. I once had a student who told me, you know, this is a stupid way to do Edwards machine. In high school, I was taught a much cleaner way. I'll mention this just in case you've ever seen it. I don't like it, but I've done it. Third was, once you've written down Newton's second law, you've got algebraic equations. Actually, personally, I put in a 2.5 here. I count the equations and count unknowns before I start doing any algebra on it. If what I'm about to say bothers you, don't pay any attention. It bothers me, actually. But this is the way people, this guy told me that he was taught in high school. To take Atwood's machine, spread the whole thing out. So I've got M2 over here and M1 over here, like that. Now I have a system whose total mass is M1 plus M2 is being pulled to the right by gravity, M2G, and pulled to the left by gravity, M1G. And I don't need to fuss with the tension at all. I've just got a net force, M2 minus M1 times G, acting on a total mass, M1 plus M2. And the answer is immediate. If you like that way of doing business, I guess it's okay. I don't like it because it's, you know, gravity is pointing to the left on one side and it's pointing to the right on the other side. What's going on here? Well, it's that the person who thought it up knows that they were originally talking about a system like this, in which it was wrapped around a pulley and so on. Were you taught that way of doing it? Anybody? No. Good.
For the way you set it up now, are both the A's, even though they're opposite direction, positive?
Yes. Well, or else they're both negative, depending on which sign, which is larger, M1 or M2. You can get into problems usually when there are 6 pulleys. You've seen the, what do you call it, block and tackle in sailing, or in which, you know, a rope goes over a pulley and under another pulley and around a third pulley and so on, so that you're pulling the acceleration of the thing you're eventually pulling on is not the same as the acceleration you're pulling down. There are cases like that, in which case then I would probably switch over to the system of calling each acceleration A1, A2, A3, and at the end of the, when I've got all those written down, see if I can find a geometrical relation among the A's. But usually it's simple enough to put it just directly like that. What are we up to? 4. A variant on Atwood's machine, actually a little bit simpler than you think. This is when I have one mass hanging down and the other one sitting on a frictionless table. And here's the pulley. And here I have a mass hanging. So this is M2 and this is M1. In that case, I would like to know what's the acceleration. Again, the whole system is going to accelerate as 1, but this time, this guy is going down, this one is going to the right. But the acceleration has got to be the same, right? Because the 2, they're attached by that piece of string. Okay? What do? Draw the 2 subsystems. Here's M1, here's M2. What forces act on M1? You tell me.
Tension.
Tension, very good. Pulling to the right. What else?
Weight.
The weight acting down, M1G. It's irrelevant to this problem, but the force acting on it. What else?
Normal force?
Normal force acting up. Anything else? I don't think so. If I put friction into the problem, that would complicate it a bit, but there is no friction here. How about M2? What forces act on it?
Weight.
The weight acting down, M2G. What else?
Tension.
Tension pulling up. Same tension?
Yes.
Yep, because that's a massless, frictionless pulley there, and the rope is massless. I didn't say it, I was assuming. So there's T. Anything else? Nope, that's it. Okay. Write the equations of motion. Oh, wait a minute. I better make a guess. What direction do I think the acceleration is going to be? Actually, in this case, it's no guess at all. I know that this one's going to go down, and this one is going to go to the right. Right? So if that comes out negative, you know you made a mistake somewhere. How about in the vertical direction for this one? What does F equals ma tell you in the vertical dimension for the block that's on the table here? It just tells you that n is equal to mg, right? Because it's not accelerating in the vertical dimension. So there's one of those typical cases where n is equal to mg, but it's not relevant to this problem, so I won't even bother to write it down. The action is in the horizontal direction. The net force is T. That's the only thing. Horizontally, that must be the mass of this one, m1, times its acceleration. Simple as that. Now I come to this one here. Forces acting on it in the positive direction, m2g minus t acting up is equal to m2 times a. Not m1 plus m2, just m2. That's the mass of that object. Now I put the 2 together. T is equal to m1a, so this says m2g minus m1a is equal to m2a. If I pull the m1a over to the other side, I've got m2 times g is equal to, actually, m1 plus m2 times a. And now if I divide through by the m1 plus m2, I get a equals m2g over m1 plus m2. A little bit simpler than the Atwood's machine in practice, a little more complicated maybe conceptually. That's going to be positive no matter what, depending on the masses. Okay, the inclined plane, granddaddy of all of these Newton's second law problems. By the way, for some reason in the business, these are called free body diagram problems. Each one of these diagrams is called a free body diagram. Don't ask me why, but if you're looking in the books, they're going to say you can classify these as free body diagram problems. So we're up to number 5. Whoops. Frictionless inclined plane, here it is. Tilted at an angle theta. I've got some kind of a box on there, mass M. It's going to slide down the incline. No friction. If it slides down the incline, what's the acceleration? Well, this time there is only one object in question, but let's draw the so-called free body diagram here. There it is, M. You tell me what forces act on M. Gravity. Straight down. mg. What else? Normal force. What direction? Not straight up, perpendicular to the surface, right? So straight up relative to the surface, if you like, but perpendicular to the surface. There's the normal force. Here's the surface, just to remind you. Surface there, and the normal force acts perpendicular to that surface. Normal forces always do. Anything else? Nope, that's it. Those are the only two forces acting on this object. Now I have a choice. I've got one force acting straight down, the other one obliquely off to an angle here. This is a two-dimensional problem, and I'm going to need to write Newton's second law in each of two perpendicular directions. Which perpendicular direction shall I choose? I could do it parallel to the plane and perpendicular to the plane. Then the n will be easy, but the mg will be ugly. Or I could do it horizontally and vertically, in which case mg will be nice, but n will be ugly, and I'll have to resolve it. Which way shall I do business? Very subtle point here. You could do it either way. You can resolve those, I can resolve the forces along any two perpendicular directions I want. Neither horizontal, vertical, nor parallel and perpendicular to the plane, if you care to, although that would be a really nasty problem. There's, in this problem, one nice way to do it, and one not so nice way to do it. And this is very often the case. What's the direction of the actual motion? Let's stick in the acceleration the way that I did before with green chalk. Here we are. What direction is the acceleration?
Parallel to the plane.
Parallel to the plane, right? It's going to be in this direction here. Therefore, parallel and perpendicular to the plane is the better way to resolve the forces, not horizontally and vertically. Why? Because if I do parallel and perpendicular to the plane, A and N will already be set up perfectly, and I'll only have to resolve mg. If I did horizontal and vertical, mg would be great, but I'm going to have to take components both of N and of A, and that's more work. So the simple way to do business is to resolve the forces parallel and perpendicular to the plane, anticipating the fact that that's the direction that A is, parallel to the plane. Make sense? When we come on Monday to study the banking of a curve, by the way, the diagram will look exactly like this, but I will draw exactly the opposite conclusion. So it's a question of analyzing the particular problem in question to see which is the best way. So I'm going to do it parallel and perpendicular to the surface. That means that I should resolve mg parallel and perpendicular to the surface. Components there. Uh-oh, what is the component parallel to the perpendicular to the surface, and parallel to the surface. Can you read those off? What's this component here?
mg times cosine.
mg
Cosine.
cosine theta. This being the angle theta. Well, wait a second. Am I damn sure that is the angle theta? Theta was the angle of the... It sure looks like it's theta, doesn't it? I bet it is. It's the kind of small angle. Let me pause there and give you a piece of profound advice. When you're drawing a diagram, never ever draw an angle of around 45 degrees. Always draw a nice acute angle on your triangle. Why? Because then I can spot just by eyeball what is the same angle. This is obviously not the angle theta. The only question is this the angle theta or is that the angle theta? Because I drew it with a very acute angle, I can tell just by eyeball which is theta. Suppose you had drawn this as a 45-degree triangle like that, and then I would have had this over here, or as close to 45-degree angle, and then I had said, you know, when I resolve this, which angle is the angle theta in this diagram, you wouldn't know visually which one it is. Do you get my point? So the moral of the story is avoid anything close to 45 degrees when you're drawing the diagram because you may well use the wrong angle there.
Both angles are theta.
If it was exactly 45 degrees, then it wouldn't matter. But you say, you know, for a generic angle like this, if you're trying to do it generically for any old angle, do not draw that angle close to 45 degrees because then you're going to have a hard time reading your own diagram. So make it very far from 45 degrees, and then you probably won't have a problem. I'll tell you another secret. I don't know another living physicist who does business this way, but I have found a very powerful way of doing problems like this where I'm trying to figure out, is that the same angle as this one here? It's a rule that I learned in geometry, but it's a sort of throwaway theorem in geometry that nobody ever remembers. But take it from me, it solves practically every geometrical problem you will ever encounter in physics. It's uncanny. The rule is this. Two angles are equal if they're perpendicular right side to right side and left side to left side. Did you ever encounter that? Sounds like some of you did hear that. Two angles are equal if they're perpendicular right side to right side and left side to left side. The right side of this one is horizontal, by right side. I mean, stick your eyeball at the vertex. Look out there. This is the right side and this is the left side. The right side is perpendicular to the right side of this one. The left side is perpendicular to the left side of this one. I don't know what to say. If that's something that helps you, as I say, that's the rule that I always use for these things, and it always seems to solve. What?
Can you repeat that?
Yes, two angles are equal. If they are perpendicular right side to right side and left as I say, I don't want to impose that on you because this is my personal way of doing it, and I don't know anybody else who does it that way, but I found it to be fantastically powerful. It's the only rule I ever remember for getting the angles right. Anyhow, this is the same angle theta. Let me just write down what the final answer is. In the direction parallel to the plane, then I've got mg sine of theta pulling down, and nothing else. Mg cos theta just kills n. So in this problem, n is mg cosine theta. Why? Because there's no motion perpendicular, so the net force there must be 0. Down the plane, I've got mg sine theta. That must be the mass of this thing times its acceleration. The m's actually cancel, and I conclude A is equal to g times the sine of theta. That's the acceleration of an object that slides down a frictionless plane. Okay, how am I doing? A couple of other examples, but I'll do those on Monday.